Hello everyone, today we are looking at another Leetcode problem. This is 1751, maximum number of events that can be attended, number 2. This is the second problem in its series. The first one was problem of the day yesterday. I will have the video link for that problem in the description. So let's get started with this problem. In this problem, we are given a list of events which has the start and the end to tell the duration of the event. It also has the value that you get by attending that event. Now, this problem is slightly different from yesterday's problem where they said that you can pick any event and it's only even if the event is 3 days long, you are going to attend only for a single day. So you could join in any of the event in between or at the start or the end, anything was okay. But here what they say is that once you take up an event, which means once you start the event at the start point, you are blocked till the end of the event. And the value that you can get from that event is the total value for that windows. Like for example, if you take this event 0, then this is a 2-day event. And if you take this 2-day event, even if if you were doing it with the earliest setting, if I could take the event 0 on day 1, get 4 points, and take event 2 on day 2, then I could get 5 points, right? But that's not how it is. You are basically blocked for this duration. If you take event 0, you cannot take event 2, even if this was 10 points. Okay, so you have to choose the event that you will have to pick in order to maximize the value that we can earn. Now, another thing that they've given us is an integer value k, which is the maximum number of events that we can attend, which means now there's an upper count on the number of events that we can attend, which means it's an optimization problem. We will have to pick the best events in order to get the maximum sum. So because we will have to try out all possibilities, this problem goes into the realm of DP, dynamic programming. Okay, so let's think about this problem a little better, right? So what is it that we do? Let's say, let's try to maybe formulate this problem with a recurrence and then build on top of it. So what happens is, let's say my recurrence function is f. Okay, and what we are doing is we are going to be iterating through this index. Okay, so maybe I can call it my events pointer, keeping it consistent with yesterday's problem. So this is something that is gonna keep growing. Now let's say I am at 2. So what is the event that is starting at 2? It is this event. But I cannot pick up this event, right? Because my current event has not ended. So then maybe I need a last event value or last event, or let's say just the last end value, which is what was the end time of the last event, so that I can pick the next event if the start was greater than the end. So I can certainly pick this event because the start is greater than the end of the previous event. So that is the purpose of this one. And then another parameter that I'll have to take care about is k. And then finally I will have my dp. Okay. Now what that means is, let's also think about the end cases. So if my events pointer at any point of time reaches the end, okay, then I cannot proceed any further, right? Or I cannot proceed any further in the sense I cannot pick any more events because no more events exist. So the value that I will get out of this is just 0 from this point. Or the second condition is if my k has become lesser than or equal to 0. which means even if there are events available, I'm not able to pick them because I have exhausted the number of events that I could take. So at this point of time, the recursion ends, returning just 0. Other than that, we can do a check if this pair exists in DP, we can just return that. Okay, let's also write that so that we have like a beginning pseudocode, right? So if events pointer comma last n comma k in DP, return DP of events pointer last n and then k. Okay, now these are the initial lines of codes. We are done with that. Now what we will have to do is, at any point of time, let's say I am at 2. At 2, I have to decide whether I should take this or not. Okay. Now, at 2, I can decide whether to take this or not. For a take, I have to satisfy the condition that the start must be greater than the end of the previous one. Okay. But let's say when I was at event 0, again I was faced with the condition take or not take. So when I selected or when I took this block, then the next block has to satisfy the condition. But let's say I did not take this block, then this one is free to be taken. Alright. So there is a little bit of the dependency that I will have to take care of. So I would have to say if the first let's fetch the values. So start comma n comma value is equal to events of events pointer. Now if start is greater than last n, then I can take this value, so which goes on a recurrence again, and I say go to events pointer plus 1, and my end now becomes, because I have taken this value, right, so it is updated to this end, and k becomes minus 1 because I picked one value. DP goes as it is. If this does not happen, then my take is equal to 0. Let's also quickly write don't take. So my don't take is I continue, my last n remains the same, my k remains the same, my dp remains the same, and finally my dp of events pointer last n comma k is equal to max of take comma don't take. Okay, this is what it's going to be. Now let us look at the complexity of this, right? So without using DP, it's clearly going to be an exponential problem. But let's see what happens when we use DP in this setting. So when we use DP in this setting, the range of this dimension is n. The range of this dimension is also n because these are indices, and the range of this is k. So what we get is something that would take n square k. Now, if you look at our constraints, n can go up to 10 power 6. And if we have to do something that takes n square, this solution will very easily get into TLE. So we will have to optimize this part. Okay, we'll have to reduce 1n. K is okay, 1n is okay. So we will have to reduce 1n from this set. Now clearly we cannot get rid of events pointer because we need to keep moving forward. So can we get rid of the last n? The answer to that is yes. So what's happening is that we have our events which should be sorted. If it isn't sorted, we should sort it because we are processing them by the start time. Okay, so you have start, end, value. Okay, let's say 1 1 1, and then you have S2, E2, V2. And now, so if I am picking one, let's say if I am attending this event, okay, there is a possibility, let's say if this event was something like that, the second event was something like that, and the third event was something like that, and the fourth event was something like that, okay, and I need to discard this, and just because I want to discard this, I have to send the last end value, which is the end time of the previous selected event. So because I need to compare that with this one, I need to compare that with this one, I need to compare that with this one. And then finally, at some point of time, where this will satisfy with this one, I'll be able to pick this. So instead of sending another dimension here and just exploding the state space, how about I do binary search and identify the next largest value from here. So the index of the next largest value from here. And in take, I will directly send, instead of sending this, I will directly send the next pointer value, which is coming from binary search. That way, we will be reducing one extra dimension and our efficiency of the algorithm will be much better. It will be n times k. Only thing, for every n, now since we are doing binary search, we will have to add log. So let me just write it up here quickly. So you are processing through all of the events, and as you're processing every event, you are also using binary search. So n log n times k is what your final time complexity will be. Okay, so that is it for the logic. Now we can look at the code so that you can see how this can be implemented. So let's start with the function max value. Here we take events, which is list of integers, and we also get k, which is an integer value, and we have to return the maximum value that is possible from attending these events. So the outcome is also an integer. Okay, we first start with sorting these events, and then what we will do is let's write our helper methods. Okay, so let's have a binary search here which takes the last n that we wanted to pass in our recursion, but now we will use that to find next possible index, a valid index. Alright, so start is equal to 0, end is equal to length of events. While start is less than end, you take mid is equal to start plus end by 2 if events of mid of 0, the start value, is greater than the last n. Then let's say we were here, okay, and we identified somewhere that this value is greater than the n. So there is a possibility that this in itself is the next possible index, or we can keep moving left and find a even lower or the immediate next possible index. Okay, so we have to now move to the left. So let's do that. End is equal to min, else start is equal to mid plus 1. And finally, we will return start, which is going to be the immediate value greater than the last n. Now, what happens if your last end itself was the last index, right? So this is where we need to let this be equal to the len of events, because we don't want to again send the last index as the answer. We want to send the last index plus 1, and the last index plus 1, the outer bound index, will get handled in the recursion call. So let's see how that would work. So let's write this def recurrence, okay, and we get events pt, we get k, we get dp. That's all this time. Now we'll check if events pt is greater than or equal to len of events, or if k is lesser than or equal to 0, then we got to n. No more cases to pick, so return 0. Next, check if this value is in dp. If events pointer comma k in dp, then return that. Return dp of events pointer comma k. No need to process this again. Now let's come to the take case. Okay, so our start in and value is what we are looking at, events of events pointer. Okay, now for selecting this event, I have to find the next event that starts after this end. So let's do that here. Next event pointer, let's write it neatly. Next event pointer is equal to binary search of end. So this will help us find the seal. Alright, and so we can happily take this recurrence of next event pointer comma k minus 1, one thing is taken, dp plus value gets added. Then we come to don't take. Don't take. So we say don't take is equal to recurrence. This is okay to just do events pointer plus 1. K doesn't changes, dp doesn't changes, that's all. And finally, the dp of this call, which was events pointer comma k, is going to be equal to max of take comma don't take. And so I can return this dp, which is events pointer comma k. Finally, call this recurrence. Starting from 0th index, complete k, and dp is equal to empty dictionary. So that's about it. And like I said, we are looping through every index, and for every index we are doing a binary search, and then the other parameter is k. So the overall time complexity is going in building the dp itself, which is n times log k, log n times k. This is the time complexity. That is it for this problem. Hope it made sense. I'll see you again with the next one. Thank you. Bye bye.